little bit about friction over the last couple of days is that we've been solving those multi-force problems. But when we have talked about friction, we've just talked about it as a value, a magnitude of friction. I've told you, in fact, in that practice quiz that we just wrote, we told you that the magnitude of the force of friction was 30 newtons. Today we're going to go a little bit deeper into friction, learn the different types of friction, and learn how to find what that value, that 30 newtons in the example question, would be. We're going to define, first of all, two types of friction. First type is called kinetic friction. Kinetic friction is a force of friction that acts against an object when it's moving. So an object is moving, is sliding, like, maybe you push your desk and it slides across the floor for a couple feet before it comes to a stop. That would be kinetic friction that caused it to come to a stop. The force of friction acting on an object when it's already moving. Now, another term that we use to describe kinetic friction, also known as dynamic friction. You'll see it written as both. I'm going to put another one. This isn't really a name for kinetic friction, but it's a name that I sometimes use because I think it helps to describe nicely what's happening. I'll put a little star by that, though, so you know that it's not actually an official name. Sliding friction. That'll become evident a little bit later on as to why I like to sometimes call it sliding friction. So it's the force of friction that's acting on an object that's already moving. It resists the motion. It wants to slow it down. It wants to stop it. Now, what do you think kinetic friction would be dependent upon? Like, in other words, we have a value of 30 newtons acting on a particular 25 kilogram box. Okay, what would affect the value of that friction? What would make it bigger or what would make it smaller? Sorry? Yes, the surfaces that are in contact with each other. You guys know that a curling rock on ice would have less friction than a curling rock on pavement. Rubber tires on pavement would have less force of friction than rubber tires on ice. All-season tires have less friction on ice than winter tires have on ice. You guys know that? Winter tires have more friction on ice than all-season tires have, not because of the tread. Why do winter tires have more friction on ice than all-season tires do? It's the type of rubber that's used. The type of rubber, it's a little bit softer, and it's the type of rubber just grips to the ice better than all-season tires do. The downside to that is you don't want to run those winter tires all summer because it's softer and they wear a lot quicker, right? But below about 7 degrees Celsius, they grip better than the all-seasons do. So one thing that affects the amount of friction is going to be the materials that are in contact with each other. We're going to call that the coefficient of friction. The coefficient of kinetic friction. The bigger the value of the coefficient of kinetic friction, the more two things stick together. Let me give you an example. The coefficient of friction between let's just say tires and ice. Okay, it's not a whole lot different for winter tires than it is for summer tires, although it is better. Okay, the coefficient of friction for rubber and ice would be somewhere in the range of 0.15-ish. The coefficient of friction between rubber and pavement would be about 0.8. The higher the number, the more they stick together. So the coefficient is higher for rubber and pavement than it is for rubber and ice, because rubber and pavement stick together better than rubber and ice stick together. Does that make sense? It's a property of the two materials that are in contact with each other. What else? What else would affect friction? The weight of the object, yes. We're going to say actually the mass of the object, okay, but certainly the weight and the mass are related to each other. You guys learned the other day the difference between weight and mass, right? Mass is the amount of space an object, sorry, not the amount of space, but the amount of matter that something possesses, whereas weight is the force of gravity that's acting on something. Okay, they're related to each other for sure. Let's say the mass. The mass affects it. Anything else? Inertia, you say? No, inertia actually doesn't affect the amount of friction. If a car is traveling at 100 kilometers per hour, a car is traveling at 5 kilometers per hour, the friction acting on the car would be the same. Doesn't make any difference. Actually, that's not inertia. That's speed. Yeah. Okay. And actually, inertia. You could make the argument, yes, inertia would affect it, but that's because inertia is related to mass, right? So let's kind of tie those two in together, okay? The speed, it doesn't. Okay, I answered a question that I was expecting somebody to say, but I just answered it a little too quickly here. Let's pretend that somebody said speed. No, speed doesn't affect friction. A car traveling at 100 kilometers per hour would experience the same friction as a car traveling at 5 kilometers per hour, as long as they were the same mass, and therefore have the same inertia. Anything else? People have this impression that surface area does. The surface area matters. So if you have a box that has a small surface area, it would have less friction than a box with a big surface area. Guess what? Doesn't matter. Doesn't matter. These are the only two factors that matter, almost. We will deal with one other slight factor a little bit later on, but for now, it's only these two factors that matter. Let me give you an equation right now for the force of kinetic friction. We'll say FKF with two lines on the side of it. What does that mean? Two vertical lines on the side of that. Nick? Absolute value, yes. So when we calculate this force, we're only going to get the magnitude. It is a vector. The force of kinetic friction has a direction. But this equation isn't going to tell me what the direction is. It's only going to give me the magnitude. So the force of kinetic friction is equal to mu k. That's the coefficient of kinetic friction. The 0.15 for rubber and ice, the 0.8 for rubber and pavement. Okay, whatever that number is. Mu k times Fn. What does Fn stand for, you think? Not the net force. No. Good guess, though. Good guess. Fn would stand for the normal force. Remember we've talked about the normal force, right? It's the normal force pushing up. Now, usually the normal force will be m times g. Why will it be m times g? Well, because usually the force of gravity and the normal force have the same value, right? If gravity is m times g, m times 9.81, then the normal force would be m times 9.81 as well. That's not always the case, but usually, at least for now, that will be the case for us. That's why we said that the force of friction relates or is dependent upon the coefficient of friction and mass, and that's it for now, because the normal force is usually m times g. Occasionally, the normal force has an angle in there, a theta in there. So there is something else that can affect it, and that is an angle, but we'll deal with that when it comes time. Okay, that makes sense? So what affects friction for now? It's going to be the coefficient of friction and the mass. Really, it's the coefficient of friction and the normal force, which sometimes has more than mass in there, but for now, it's just going to be mass. Make sense? That doesn't seem too bad, does it? Well, let's do a problem. Example number 5. It says a 1,700 kilogram car is skidding on pavement. The coefficient of kinetic friction between the rubber tires and the pavement is 0.80. Determine the force of friction acting on the car and the acceleration of the car. Now, notice this car is skidding on pavement. Sometimes cars just drive on pavement, right? Sometimes cars spin their wheels on pavement. The reason that I sometimes call kinetic friction sliding friction is because in order for it to be kinetic friction, it actually has to be sliding or skidding like this. Ironically, the force of friction that gets a car moving, right? There's friction between tires in the road that gets a car moving, right? That's not actually kinetic friction. Okay, that's not, the car is moving, but it's not sliding. It's not skidding. Okay, the wheels are turning. In order to be kinetic friction, it has to be sliding or skidding. We'll see some examples to differentiate that a little bit better as we go through this. Okay, but that's an important word. It's skidding. When it says skidding, we know it's kinetic friction. Even if it didn't ask us for the force of kinetic friction, we would know this was kinetic friction. Okay, so let's write down some givens here. We have a mass of 1,700 kilograms, and we have a coefficient of kinetic friction. By the way, this letter for the coefficient of friction, I should have clarified that a little bit earlier. It kind of looks like a U. It kind of looks like an M. Right? It kind of looks like a U, kind of looks like an M. It's a Greek letter. You know what it's called? It's a Greek letter called mu. Do you know why the Greeks called it mu? Because it looks like an M and a U, right? Now, I think the Greeks might have had it first. But that's the way we're going to remember it. It's not why the Greeks called it mu, but that's the way we're going to remember that it's called mu, right? Because it looks like an M, kind of looks like an M, and it kind of looks like a U. Okay, does that make sense? I don't know. This confuses me sometimes. It's all Greek to me. The coefficient of friction is 0.80. The force of friction is what we're looking for, and it is kinetic friction. Not that you guys know any other kind of friction right now, but we're going to call it, we're going to specify that it's kinetic friction because there is another type that we're going to deal with here soon. All right, so let's say the force of kinetic friction is equal to, well, technically it's mu times the normal force. But what do we say the normal force is almost always equal to for us? Yeah, mass times gravity, right? My coefficient of kinetic friction, which has no units, by the way, is 0.80. My normal force, as Martin just said a minute ago, is 1,700 kilograms times 9.81. Now, we're just going to make that positive 9.81 here because we're only looking for a magnitude. So 0.80 times 1,700 times 9.81 meters per second squared. Let's figure out what that is. Gives me a value of 13,341.6 newtons. Now we're going to round that to how many digits? This would be 4. This would be, how many is this one? 2. 9.81 we used, right? That's 3. Final answer should be what? 2 digits, right? So let's underline these 2 digits, the first 2 digits, and then let's put a little arrow at the third one. We're going to make it 1 point. The third digit is a 3, so the second digit rounds up or down? Rounds up or down? Down, yeah. 1.3 times 10 to the, what is this? 1, 2, 3, 4. 1.3 times 10 to the 4 newtons is our answer. Now, which way is it? Well, I don't know if it's right or left or up or down or what, right? I just know that it's opposite to the way that it's moving. It's moving to the right, friction's to the left. If it's moving to the left, friction's to the right. Now, how do you think you're going to find the acceleration? You have the force. The force is with you. Now you just need to know what to do with the force, right? It's kind of like Luke Skywalker has the force, just doesn't know exactly what to do with it. Goes to Yoda, gets a little help. Yoda teaches him how to use the force. A little Jedi training here. Okay, that's where we're at right now. Okay, we got the force. We just need a little help from Yoda to tell us what to do with the force. What would Yoda say now? Let's make this green because Yoda's green. What would Yoda say right now to find the acceleration? He would say do or do not. Do or do not. There is no try. What would he say here? Yoda would say, you got the force, use the force divided by the mass. F is equal to m times a, right? Now, technically that's a net force, right? But the only force we have in this problem is friction, so the friction is the net force, so we can do that. Let's use our unrounded number, 13,341.6 newtons divided by the mass, which is 1,700 kilograms, which means our answer for acceleration is 7.8 meters per second squared. Good? Good? Almost. I missed something here. It's subtle. Man, it's subtle, but the magnitude of the force of friction is 1.3 times 10 to the 4 newtons. But if this car is skidding on pavement, this car must be slowing down, right? Right? Which means the magnitude of the force of friction is 1.3. But the actual force of friction when we drop the absolute value signs is negative 1.3, which means the acceleration is negative 7.8 meters per second squared. Does that make sense? Well, that's tricky, hey? Okay, look though, look at the difference between what we call the force of friction here and the force of friction here. Absolute value signs, we're just going to calculate the magnitude, but we don't want the magnitude right here. If we have the direction, we want the direction. And because it is backwards, it always will be backwards, we have to make it a negative value there. You guys have had a chance to work on the worksheet for a few minutes. Let's take a look at question number 2 from that worksheet right now. See how it went for you. Number 2 says a 100-kilogram object moving at 20 meters per second comes to a stop over a distance of 40 meters. What's the coefficient of kinetic friction that acts between the object and the ground? For this question, we're going to say our mass is 100 kilograms. We're going to say that VI is 20 meters per second, and we're going to say that VF is 0 meters per second. Because it comes to a stop, right? It says it comes to a stop over a distance of 40 meters. Our displacement will be 40 meters. A lot of times we're given the coefficient of friction, but here we're asked to solve for the coefficient of kinetic friction, or the coefficient of dynamic friction, or sliding friction, whatever you want to call it exactly. Some people look at this and say, I don't know. I don't have anything that ties all this stuff together. Listen, one of the things that I want you to learn as we get further and further on in physics is that givens are important, but they're not the most important thing. The most important thing is just thinking about the question. Like what's going on in this question, not givens. Okay? Givens are important. They're going to help us, for sure. But if we just look at the givens and look for an equation to match those givens, then it's sometimes going to lead us down the wrong path. We get this tunnel vision sometimes for our givens, and we want to avoid that. Listen, this is a friction problem. This is a friction problem. I want to find a coefficient of friction. There's only one thing that I know to do when I have, or am looking for a coefficient of friction, and that's use this equation. F is equal to mu times Fn. I'm not worried about my givens right now. I'm just looking at the problem. This is a coefficient of friction problem, and this is the only thing I know to do when I'm looking for or have the coefficient of friction, period. Don't worry about the mass and VI and VF and all that stuff. Worry about this. That's the main part of this problem right now. Now let's rearrange the solve for this. The only thing I know to do. So you might be the same as me. If I was looking for this question for the first time and saying, geez, I don't know exactly where I'm going with this. I just know that this is valid, so let's do it. Let's try it. Then I look at this and say, well, okay, I know the normal force. The normal force is m times g, right? So let's say it's FKF over 100 times 9.81. Does that make sense for the bottom one? Yeah, the normal force, that was the same as our example, right? 100 times 9.81. But the coefficient, sorry, the force of friction, I don't know what that is. So I got to find that some way. I got to find that some other way. There's only one force acting here, so the force of friction would be the net force, which is equal to m times a. Okay, that's valid, isn't it? But I don't know what a is, so I got to find a some other way. I'm going to say VF squared is equal to VI squared plus 2AD. Hold on for a sec. I'm going to rearrange that to solve for a. Gives me VF squared minus VI squared over 2 times d. Solve for a there, and then sub it into here. multiply by the mass, get force. Wait a second, now I have the force of friction. Plug it into here and solve for the coefficient of friction. Does that make some sense? Okay, so your homework for the weekend is, of course, the quiz that is on those multi-force problems, but also questions 2 and 3. Only questions 2 and 3 from that worksheet.